Hi and welcome to MSc. In this video we're going to be looking at the bonding triangle. So to fully understand the bonding triangle we need to quickly recall electronegativity. So this is the relative measure of the attraction an atom has for its shared pair of electrons, right? So when it bonds and it's sharing a pair of electrons, how much of a pull does it have on those shared electrons, right? And this is always going to be in the table somewhere for you. Here's one from the IB data booklet. You can see it has other information, but underneath it has the electronegativities values, right? So for carbon it's 2.6, for example, right? So this will always be tabulated somewhere where you can go and look it up or be provided for you in a question. Electronegativity might also be referred to as like the Pauling scale, after the scientist who did some work with this. This is a relative scale, so they're unitless values. The other thing we need to recall is the electronegativity difference. Now this is the difference in the electronegativity values of the two atoms that are sharing the electrons. And generally, this helps us kind of classify compounds as either ionic or molecular. And we'll take a quick run through of some examples of this to refresh your memory on how that works. Quickly though, electronegativity can sometimes go by the Greek letter chi, or you might just see it written as En for electronegativity. And then of course the electronegativity difference, you can either see it as the delta chi, or you might even see it just as delta En, depending on the teacher and the course that you're in. Down below here we have a scale that shows the electronegativity differences. So up here, this is the biggest difference that we can have, and this difference would be resulting from fluorine and francium. And if you recall, electronegativity differences increase going up a group and increase across a period. So we get fluorine being the most electronegative. Okay, notice there's no values here for the noble gases because again they don't usually engage in sharing electrons or bonding. So let's work backwards from here. At this point here, roughly 3.2, that's often when we say things are 100% ionic. Over here, at around 1.8, again this will be a little different depending on the source, maybe as low as 1.6 or 1.7 all the way up to 2. This is generally the threshold that distinguishes between ionic and molecular. So in this region here you would have an ionic compound. Okay, below 1.7 we would typically classify it as a molecular compound. In this region, between about 1.8 and about 0.4, in this region is where you'll have your polar covalent molecules. Okay, the 0.4 is typically the carbon-hydrogen electronegativity difference, and so when we get to organic molecules, when we have electronegativity differences of about 0.4 or less, we're not super worried about the compound being polar. So we would list this section here to be just the covalent. Okay, again, this whole region here are all molecular compounds. Okay, and then of course to get the zero difference, we are typically going to have diatomic molecules at this point, so things like N2 or O2 where they share perfectly well. There are some other substances that can have electronegativity differences of 0 as well. And you can explore the electronegativity chart and see which compounds might do that as well. So this is a pretty good rule of thumb. It works fairly well for a lot of high school chemistry, to be honest. But we do start to see some problems with it. If we start to think about, well, metals that bond, like copper, for example, just a copper metal, well, it has electronegativity difference of 0, but it's not really a diatomic molecule. So something weird's happening with metals. And so maybe you've done some research about metallic bonding and how it's a lattice of positive nuclei with the sea of delocalized electrons. So how does that fit into this? You might have seen some species around the 1.8 threshold that might behave very ionically but also have some covalent features, or vice versa, and some weird stuff happens around there. And of course this is a spectrum, right? And so looking at it as a spectrum, meaning that okay, it gradually changes, this isn't a magical threshold, can help, but it doesn't necessarily fully tell the whole story. So that's where the bonding triangle comes in. So here is the bonding triangle. This image is from the IB data booklet, And what we have, instead of it being a line like we used before, that line is actually now represented along the y-axis. And you can see this difference in electronegativity is this axis. Whereas down here now we have our average electronegativity, because of course the electronegativity that these species have will influence its bonding type. So some things we can still see on here. We can see now that we have metallic bonding that does occur and is represented on this, which is important and useful. We still see thresholds where we can kind of distinguish between ionic and polar covalent, but again we have to understand that there's not maybe a magical line that it crosses there. We can start to see why at about 1.8. In the past we would have said, well, look, it's mostly ionic at that point, right? Even though it could still have some polar covalent influences. And we can see down here when we get below about 0.4, we have very little ionic properties. We're probably going to be in the covalent property and no longer really being considered polar covalent. So I'd like to do a couple examples of utilizing this to plot some species on here. So I'll try to do 3 quick examples. The first example I'll do is sodium chloride, NaCl. Okay, and looking this up in the data booklet, we can see that the electronegativity value for sodium is 0.9. Again, not very electronegative because metals typically don't want to pull on that shared pair very much, whereas chlorine is quite electronegative at 3.2. So this leads us to have an electronegativity difference in this scenario equal to the 3.2 minus the 0.9, which leads us with a difference of 2.3. And in the old scale, you definitely classify that as ionic. Be right almost kind of where that line is there, right? Let's look at though where it is on the average. So when we look at the average value here, this is going to be 3.2 plus 0.9, all divided by 2, we get a value of 2.05. So we're right around the 2 value here, and I would say we are probably right about here. So there is your NaCl. Okay, let's take a look now for another example. I won't work this out in full, although it'll be the same process. We're going to look at H2O. So specifically here, we're looking at the hydrogen-oxygen bond. And if we do that, we get that the change in electronegativity, and I encourage you, if you want to pause the video and try these out with your values, you can go ahead and do that. But for the difference, we get a difference of 1.2. And for the average here, we get a value of 2.8. So the average is along here, 2.8, right about here somewhere, and it goes up to 1.2. So we are more or less right in here. There's your water. And then lastly, I'll do one that's a bit of a different example or a little bit more unique, and that'll be the aluminum oxide. And this example you might have used in the past when looking at the period 3 oxides. It has some unique properties. So we look at the change in electronegativity between, or difference rather, between aluminum and oxygen. We get 1.8, which was right on that threshold from before. Then if we look at the average electronegativity of both of these, the oxygen being 1.6 and the aluminum 3.4, we get that the average is 2.5. 2.5 and about 1.8 is pretty much right on that border. Perhaps just on the ionic side. This one has some unique properties though. The bonds appear to be ionic, but if you remember from the period 3 oxides, this is an amphoteric species, which seems weird because a lot of the ionic species showed basic properties, ionic oxides, right, the metal oxides, and then the non-metal oxides showed acidic properties. This one shows a little bit of both. This one's also a hard substance, which is very similar to things that are like giant covalent lattices or structures like diamond. So this one's very, very hard, much harder than other ionic lattices that you'd see. So by placing it on scales like this, we can start to tell and give a little bit more information than our simple 2-dimensional axis would have had for just electronegativity differences. You feel free to compare some more and find some metallic substances and place them on here, and you'll notice that they have they fall in that metallic section of the bonding triangle. I hope this run through of the bonding triangle has been helpful. If it has, please consider liking the video and subscribing to the station. And as always, thank you so much for listening and watching.